Hey guys, how we doing today? We got chapter 10, unit 7, or section 7. We're going to be talking about dot product and the angle between the two vectors. Okay, just add another wrinkle to all the stuff we've been doing over the past couple weeks. So hopping right in, the first thing we got today is the definition of a dot product. Okay, the dot product of vector u and vector v denoted by u dot v. Okay, notice that does look like a multiplication sign, but when it's that big, dark, bold dot, that's talking about the dot product. And I guess it's more about context. Understand the context of the question. So it's denoted by u dot v is the real number. Okay, so we're going to do u1 times v1 plus u2 times v2. Okay, so we're multiplying our x components and we're multiplying our y components and we're adding them together. All right, this should just give you one answer. Okay, it's not going to give you an ordered pair. It's going to give you just one numeric answer. All right, stick with me. We'll explain why later. So, properties of the dot product. All right, you can take it both ways. You can take u dot v and it's going to equal the same thing as v dot u. All right, understanding that u dot u is the same thing as u1 plus u2 which equals u1 squared plus u2 squared, which also equals u1 squared plus u2 squared squared. So that's an interesting way of looking at our norm u, right? Because that's what's inside the parentheses is our norm u and then squaring it. So u dot u is the same thing as squaring your norm or your, remember, r. Okay, the next one's just talking about scalars and the dot product. So if you got a scalar multiple times the dot product itself, you can either do the scalar times the result of the dot product, right? Scalar times the result of the dot product, or the scalar times a vector before the dot product. But the thing is, you only distribute it to one. Notice, it's k times u or it's k times v. All right, the next one, u dot the addition of vectors. Okay, in this case, when you're going to dot it, so when we're dotting on the outside, you can distribute. Notice, right? This becomes u dot v plus u dot w. So, again, these properties, good things to write down on a study guide if you're making one. Okay, moving on. Angles between two vectors. Okay, this kind of comes into what the dot product helps us with. So the measure of the angle theta between two non-zero vectors u and v with 0 less than or equal to theta less than or equal to 2 pi is cosine theta equals the dot product of u. All right, let me write this out. Cosine theta equals the dot product of u dot v all over the norms of u, and then this is times. So yes, I can make it the star times v. Okay. See, this is where those dots can get a little confusing. I'm going to try to make stars for multiplication for this unit, and I'll make dots for dot product. Okay? So we're going to be using this formula a lot. So another one to make sure you write down, have in the back of your mind. You'll see how much we're going to use it just in these notes alone. So going to our examples. Let us have vectors u, v, and w. Okay, so we're going to be using these vectors. So write those down so I can keep scrolling and keep doing these problems because we're going to use them for the next couple. All right, so for A, we have u dot v. So let's multiply our x components. 3 times -1 plus 2 times 5 going to equal negative 3 plus 10, which should equal 7. All right, just doing the dot product, multiplying those. Okay, so for this, for B, it's just easier to add our stuff before we do the dot product. That's what I always end up doing if I can. But let's just write this out the long way, right? We have this vector. We're going to take the dot product of the addition of these vectors. Okay, so what we should get here is our 3, 2, dot, this ends up being 1, 2. Okay, when we keep solving this out, our dot product looks like 3 times 1 plus 2 times 2, which should equal 3 plus 4, which should equal 7. What do you know? Okay, going on down to 7, or C, excuse me, going on down to C. Now we're taking the dot product and we have a scalar on the outside. Okay, but look, I think we already took the dot product of UV, didn't we, up in A. So we took the dot product of UV, which gave us a 7, right? So we can just put that out front. I'm just going to put that out front. Then what's our W? Our W is 2, negative 3. So, right, this is our U dot V. This is our W. All we're doing is multiplying that out, right? Because now 7, after we do the dot product, becomes pretty much a scalar. And you get 14, negative 21. All right, not too shabby. Okay, notice how some results end with a single number, others results with a vector. Okay, that's a vector we ended with. Now going on to D, we're going to start using the angle between vectors theorem. Okay, so if we got U and V, all right, that's going to give us something that's kind of like, all right, we got one out this way, and we got one up that way. Let's see, this is our U, this is our V. Okay, so we know we're going to measure the angle between them. So let's set up our formula. Okay, we know it's cosine of theta equals the dot product, which in this case is going to be 3 times negative 1 plus 2 times 5 all over. Let me just do these out to the side. I'm going to do my norm of U and V up here first so I can plug those in. So that's going to be 3 squared plus 2 squared. That's what am I doing right here? Just going to equal square root of 13. Then my V is going to equal, that's going to be the square root of 1 plus 25, so the square root of 26. Okay? So we're going to plug those in. Our square root of 13, right? I'm just taking the norm of these vectors. Those are just those norms, or the R value, if that makes more sense to you. Okay, from here on the top, I got 7. On the bottom, plug that in your calculator, I got 18.38. All right, and if you take the inverse cosine of that, you're going to get 67.6 degrees. Okay. Remember, I took the inverse cosine of this right there to get that final answer. Right, that equals our theta. Okay. Now moving to E. Now we want to find the angle between vectors U and W. All right. So again, setting up our cosine theta. Okay, on the top we're going to have our dot product, which is 3 times 2 plus 2 times -3. Okay, that's going to be interesting up there. We already got our norm value of u, which is square root of 13. Our norm value of w we'll do up here, which equals the square root of 2 squared plus, oh my goodness, plus -3 squared. Again, is going to give us a square root of 13. Okay? So from here, when we start evaluating, I just always start at the top. Notice we get a 0 in the numerator, right? We get 6 plus -6, which gives us 0. So that means our whole thing is 0. So when we take the inverse cosine of 0, right, this is something hopefully you guys have memorized. You get 90 degrees. Okay? And if something is 90 degrees apart, we say it's perpendicular. Right? So we have perpendicular vectors right here. So, as you can see going down right below this, our perpendicular vector theorem, we talk about how every time you get a 0 in the numerator when doing your dot product or angle between two vectors theorem, whenever you get a 0 in the numerator, we know it's orthogonal, right? That's this word right here, which is the same thing as perpendicular. Okay, orthogonal and perpendicular, again, it's the same thing. Math, they just try to give you more words for different stuff. Okay, so let's just read this one out. It says two non-zero vectors u and v are perpendicular or orthogonal if and only if their dot product equals 0. So that's just saying, I'll squeeze this right down here. That's saying cosine theta equals 0 over RV times u. Okay, if that equals 0, theta equals 90 degrees. Okay, that's all that's saying. So that's just a little shortcut. That's a test, because a lot of times we want to find out, are they parallel or are they perpendicular? Okay, so let's look at 2. Find the measure of the angles between the lines. So now we have 2 lines. Okay, we don't just have vectors. We have 2 lines, and we got to find the angle between them. So let's start by looking at the slope. If you guys remember, right, the slope almost tells us our vector. Okay, that slope gives us the angle and everything. So here, let's just identify our slopes. For this guy, we got m equals 3. We got m equals 1/2. All right, we know that we can take when we have our, from vectors, we can make these rise over run, right? So this is the same thing as 3 over 1. Remember, it's our y over x. Right, so 3 over 1 is our y over x. Right, 1/2 equals our y over x. So we have our, let's just say y1 vector. We're going to call it y1 equals 1, 3. We're going to have our y2 vector equal 2, 1. Okay, notice I just took our slope and I turned it into a vector. Okay, you can always do that with the line. So from here we have a slope, and that's really all we have our 2 vectors, so that's all we need to find the angle in between. So let's do our absolute values, our norm of vector y1, which equals square root of 1 squared plus 3 squared plus square root of 10. Okay, we got our y2, which is going to yield us 2 squared plus 1 squared, which equals square root of 5. Okay, we got all our pieces. Now we can plug it into our big cosine theta formula. Should give us 1 times 2 plus 3 times 1 on top. Should give us square root of 10 times square root of 5 on the bottom. Alright, and this should give us 5 over 7.07. think inverse cosine of that, and you're going to get 45 degrees. Okay, so we had two lines. We used the slope to find our vector. From there, we just started plugging in all our stuff, all our vector points. Okay, 3. How are two vectors related if their dot product equals 1/2 of their lengths? So this wording, this problem, it's a lot more confusing than it really needs to be. All they're saying is, when they're saying how are two vectors related if their dot product equals 1/2, is they're saying what is the angle when you have this, right? Or 2/4 or 10/20, all the same thing when it's 1/2, right? When your dot product is half the products of your lengths. And remember, on the bottom, the lengths are your r's. You have the r of each vector under there, and you're multiplying them together. So if it's half, right, 1 is half of 2, the product of the lengths on the bottom. Okay, so that's just all they're saying. And what you get here, if you plug that in, your theta is going to equal 60 degrees. Okay, so if you get a half, you're going to get 60 degrees. Get 0, it's going to be 90. That's just more of a thinking problem, how to set it up based off the question. Okay, 4. Things are going to get a little bit more complicated. So we got the following vectors. We got to determine if they're parallel, perpendicular, or neither. So we're going to kind of give you a little order on how to do things. So the order, first thing, are they parallel? Right? Check to see if it's a scalar multiple. Check to see if it's a scalar multiple, okay? That's the first thing, right? We can check to see if one's bigger than the other. Is there a scalar that we can apply to it to see if it's parallel? Okay, the second thing we just did today, dot product. Find out if it's perpendicular. If your dot product equals 0, it's perpendicular. Super easy stuff. So, first thing, is there anything, what do we have to multiply 2 to get to -6? It's a -3. So if we multiply -3 to both of these, do we get the right answer? No, we don't get -9 here, so it's not parallel. Okay, check those, multiply them both by -3, get -6 and -9, that does not equal. Okay, so they're not parallel. So the next thing we have to do is try the dot product. So we got to do u dot v, which equals 2 times -6 plus 3 times 4. What do you know? You're going to get a 0. Okay, we get that 0 for our dot product, which means it's perpendicular. Okay, you could also look at it as our cosine, right? You could, if you're someone who wants to keep everything like this, right? Our cosine equals 0 over, oh boy, over square root of 13 times square root of 52. Either way, the 0 on top means your dot product 0 means it's 90 degrees. Which means it's perpendicular. Okay, so in A, they're not parallel, they are perpendicular. For B, okay, same thing. Is there something we can multiply to get to it? I'm seeing 4 or -4, right? So times -4 times -4, you get 8. Oop, that's an 8, and you get -20. So what do you know? Look, they equal. All right, so they're the same. So there is a scalar multiple. So they have a scalar multiple of -4, which means they're parallel. Okay, so parallel. And those two lines like that are all is how you do it. Another cool way is you can actually use that cosine formula to find out if they're parallel as well. Because if you do your cosine theta, you should get something that gives you negative 16 over 1/6, or negative 1/16 over 1/16, which equals a 1. So if you get, it should give you a 1. So that gives you 180 degrees. So if you ever test the angle and it's 180 degrees, or if it's 180 degrees, it means they're parallel, right? Because they're going in the exact opposite direction. Just like when we were talking about our positive and negative vectors, right? U and negative U are going 180 degrees different direction. All right, more examples. 5. Only a couple more. Okay, 5, we're going to find the value of x so that vector u equals x5 and it's perpendicular to vector v. So from this, right, we know our rules about perpendicular. We know our dot product has to equal 0. So we can set up a dot product and solve it algebraically. Right, we need our dot product to equal 0. So you end up with 3x plus 30 equals 0. 3x equals negative 30. X equals negative 10. Okay, easy as that. Understand what the question's asking, set it up correctly, solve it out. For 6, find all vectors in the plane that are orthogonal to 372 degrees. Okay, r is 3, right? This is our r. This is our r. There's our theta. And we want it to have a length 10. A length 10. Okay, so we already know they gave us r, right? What's our length? 10. They gave it to us already. And we want it to be orthogonal to 72 degrees. Okay, now we can use some tricks here. All right, we have 72. And we want it to be orthogonal, so we can plus or minus 90 degrees. Okay? If you do plus, that should give you get negative 18 degrees and you get 162. Okay, both of those are correct answers. They're both 90 degrees in opposite directions, so you can put them both. Sometimes they'll ask you for both, sometimes they'll just say you need one. That's all we have to do. If you want a little visual, our 372 degrees, let's just say it's kind of like that. Okay, that's about right. 372, that's our original point. Now, we wanted one that is length 10, right? This is length 3. This is length 10, and we want it going 90 degrees from that original one. So you plus, add or subtract 90 degrees, get your angles. Now 7, okay, we're going to do something a little bit new. Maybe you've seen this before. They want us to find all vectors in the plane that are orthogonal to vector u and have length 10. So unlike this one, well, I guess 6 they asked for all vectors too. So we're finding both those 90 degree vectors again. Okay, so we're going to use, I guess kind of what you'd call a shortcut here. All right, so think about it this way. If you got our vector 6, negative 2, okay, we need to find something perpendicular to it. So I'm just going to say our m for this is going to be negative 2, 6, right? I'm just doing my rise over run, my y. I'm taking that vector, I'm turning it into a slope. Okay, now if I want two slopes that are perpendicular, So perpendicular m's would equal, so remember this is opposite reciprocal. So opposite reciprocal means times it by -1 and flip it. So that's just going to get you 6/2. But remember, 6/2 is the same thing as -6/2. And think about that. If you just got 6 and 2, that's going up in the first quadrant, right? That slope's headed that way. And -6, -2 is just headed in that third quadrant. They're headed opposite. They're 180 from each other, but they're both perpendicular from our original slope, right? They're both perpendicular from that original slope. So now we're gonna find that r of our of this original u. We're gonna find that original u vector. Okay, we're gonna solve this thing right here, which is just gonna be r 6 squared plus -2 squared, which should get you √ 40. Yeah, it's going to equal that. Okay. So from here, now we have our new vector, right? We have our 2, 6 vector. And really, since we know that these right here, right, we know that it's just adding negatives to it. We're only going to do it to 1, right? We're going to just use our new vector as 2, 6, right? Because we did the opposite reciprocal. And now we have to scale it because they say it has to be a length 10, but we know the old length is this 2 square root of 10. So you got to do new length over old length. And then we're going to multiply it by our vector. So new length is going to equal, what? We want 10, right? And our old length is 2 square root of 10. And then we're going to multiply it by our new vector. Okay, so that's all we're doing from here. So when we multiply that, remember, it goes to each of them, because it's a point. You end up with 20/2 square root of 10 and 60/2 square root of 10. Okay, you simplify that down. I mean, you simplify it, you rationalize it. You should get, after rationalizing, you get that 10/10 and 3 square root of 10. And then you should get your final answer should be square root of 10, 3 square root of 10. All right, but remember, you got two options. You got two because we have to do our both positive and both negative because there's two of them. So then we know if this is one, right? Then we also have one that's negative square root of 10, negative 3 square root of 10. Okay, so what we did there, we found our new vector by doing the opposite reciprocal. All right, we found its other point by just throwing negatives on it. All right, giving it the 180. And then we took our old and new lengths, multiplied them by our new vector to get our two new points. All right, there's going to be some homework problems on that. Reference back to these notes to help you out. That's all I got